Hey everybody, this video is about mass moment of inertia, which is different from area moment of inertia. So let's say you had some shape like an I-beam or something, and then you want to know how this beam will bend or stretch or twist. So that is a function of the area moment of inertia. This one, area moment of inertia. So you would take a cross section of this beam, so let's say like this cross section, which is some two-dimensional area, and then find the area moment of inertia of that cross section, and then bending, stretching, twisting of this beam is a function of this. But then let's say you're hanging this beam from a crane, so there's a cable, and then let's say this beam rotates. So the angular momentum, the torque, is a function of the mass moment of inertia, like this. So see, we're integrating over mass as opposed to integrating over area. The units of the area moment of inertia, look at this, that's like meters squared. So the units are meters to the fourth. Mass moment of inertia, look at this, meters squared, kilograms, that's mass, right? So kilogram meter squared. So see, already the units are different. Area moment of inertia, mass moment of inertia. So let's discuss mass moment of inertia, but for simple shapes. Let's limit our discussion to, for now, slender bars, which is practically one-dimensional, and then in another video we'll talk about thin plates, which is a 3D object that's practically two-dimensional. Okay, so let's start with just a slender bar. For example, a bar like this is three-dimensional. It's a cylinder. But if you make the radius sufficiently small, like this, then it's practically a one-dimensional object. Right, so if we pick some coordinates, and then now let's integrate r squared dm for the mass moment of inertia. So if we have some little differential mass element, this, here, and then we integrate over its position, r. So the way I pick coordinates, r would be in the x direction, so r squared would be x squared. And then dm, let's define density, rho, as mass per volume, differentially, so differential mass over differential volume. So then dm is rho dv, the density and volume. But then the volume, if you look at this little differential mass element, if we zoom in on it, this differential mass element has some volume. This is the cross-sectional area. And then this length here would be in the x direction, dx. So this dv for volume is area dx. Okay, so dm I can replace with rho a dx. Okay, now let's make some assumptions. Let's assume, because this is a slender bar, it has the same cross-sectional area throughout its entire length. So the area is constant, meaning we can take it out of the integral. Let's also assume that it's homogeneous, so it's the same density throughout. So the density we can also take out of the integral. And if it is indeed homogeneous, where the density is constant, the density, then it's not just differentially true. Overall, the total mass over the total volume, that's the density. And then again, the volume was, it can be the cross-sectional area times the entire length of this bar, L. So the volume is the cross-sectional area times the length. And if you look at what I just wrote here, rho is mass over the area times the length. I can move this on the other side of the equation. Rho A equals m over L. So look at this. So I can take this out of the integral because it's a constant, and it's just m over L. Okay, and then we can integrate this. Let's say if we pick the center of mass, and this entire bar is length L, then let's integrate from minus L over 2 to L over 2. Okay, so that would be, let's take the 3 out of there. Okay, so L over 2 cubed minus negative L over 2 cubed. Okay, so then that's minus minus is plus, so 2 over 8, 1 over 4, so 1/12. mL cubed over L squared. Okay, so this is the mass moment of inertia of a slender bar about its own center of mass. So this is true for any slender bar. So you could just jot this down and memorize it if you want, because it's always true for any slender bar. Just for practice, let's say instead of about its center of mass, what if we want the moment of inertia about the end over here? Then we can just recycle r squared dm. Everything is the same except the limits of integration. I'll just copy that. So m over 3L x cubed from, and instead of negative L over 2 to L over 2, from this end of the bar to this end of the bar, so 0 to L. So then that'll be 1/3 mL cubed. So different. So you see the moment of inertia depends upon where you're defining it, right? So this was about the center mass. This is about the end. Notice that this is more. This is actually a minimum. The moment of inertia about the center of mass is always a minimum. Okay, let's do one more that's maybe a little more exciting. So let's say you have like an L-shaped bar. Let's just say it's length L over here and length L over here. And we want the moment of inertia about this end over here. Okay, and let's just split it up into this horizontal part and this vertical part. So the mass moment of inertia, let's split it into the horizontal part, vertical part. Okay, so the horizontal part actually looks exactly like what we just did right here. So, right, that's r squared dm. This is the horizontal part, vertical part. But then the horizontal part is only, like, this is our little differential mass element here. And we're integrating r, which in this case is only in the x direction. So it'll be x squared. And then dm again is rho dv. dv is area times, in this example, dx. And then in this case, integrating from here to here, 0 to L. Okay, for the vertical part of the bar, our differential mass element is, let's see, over here. And its position is R. So if you look at this triangle here, Right, this is L, this is R, this is the little differential mass element, which has some position Y, which is going from 0 to L. So what is R squared? Right, look at the triangle. R squared is L squared plus Y squared. Right, so R squared for the vertical part is L squared plus Y squared. And then dm is rho dv, and dv is area times dl, and in this case the only thing that's varying is y, so dy. Okay, and then this goes from, y goes from 0 to L, and then same story, this rho times A is m over L, but that's only for the mass of this horizontal part of the bar and the length of this horizontal part of the bar. And then for this one, that's rho A is the mass of only this vertical part of the bar and only the length of this vertical part of the bar. These two happen to be the same. I'll just leave it like that. Okay, and then you just integrate this. From 0 to L. L squared y plus y cubed over 3 from 0 to L, and then you just finish this, right? So that's 1/3 ml squared, and then this is these are both just L, right? Okay, so this is L cubed plus L cubed over 3, so that's 4/3. So 4/3 m 4/3 ml squared. And again, this is the mass of only the horizontal part of the bar, and this is the mass of the vertical part of the bar. Which in this case, I needed to specify the mass of the bar, right? Let's say if it's 10 kilograms, then this part would be, right, this is L and this is L, so this would be 5 kilograms here, 5 kilograms here. Okay, so this is kind of describing the concept of how to do this mass moment of inertia, but in practice, we would use the parallel axis theorem, which will be the next video coming up, so stay tuned for that one. Okay, so I'll see you in the next video.